Now let's try to derive a lens maker's formula. So see, this lens maker's formula is quite an important one because see, lens maker's formula gives us a relation between focal length and radius of curvature of both the surfaces of any particular lens. So here what we are doing is we are using a biconvex lens. Now there are certain assumptions what we are doing here. So the first assumption what we have is the lens is a thin lens. Okay, so the lens is a thin lens. This is the first assumption. Now the second assumption is the aperture is a very small aperture. Next, the third one is the object whatever we are placing is a point object. So this point object is very important. So this is not something which has a big dimension. Then the fourth assumption what we are doing is the incident angle, the refracted angle, they're all small angles. Okay, so all of them are very small. So these are the four assumptions what we are doing. Okay, and then again the sign conventions will come. So the sign convention is all the distances are measured from the center of the lens. Okay, so from the center of the lens we are measuring the distance. And the second assumption is if the distance whatever we are measuring is in the direction of light, it is taken to be positive. So in the direction is positive, and if you are going against the direction, then it is taken to be negative. So these are the assumptions what we are making, and then these are the sign conventions what we are taking. Okay, so now what we have is, first thing is we need to consider a biconvex lens. Okay, so what we have is, so imagine this to be a biconvex lens, and then now remember, so let's call this point as x and let's call this point as y. Now a very important point is, see, we need to draw the principal axis, right? So let's call this as the principal axis. Okay, so from here to here is the principal axis. Okay, now the center of the lens is, if you join xy, and if you take a point where xy, the line joining xy and the principal axis, so whatever this particular point meets, that particular point is the center of the lens. So let's call that point as C. Okay, now next thing what we have is, see, this point, call it as P1, let's call this point as P2. Now why P1 and P2 are important is we have two surfaces here. Okay, that is x P1y, this is the first surface, and x P2y, this is the second surface. So we have two surfaces. These two surfaces play a very important part in this formula. Okay, then see, we have two surfaces, so obviously it will have two radii of curvatures. Now since xp1y is the first surface, then a point somewhere here, let's say c1, will be the center of curvature for the first surface. Then similar way, here we'll have c2, which is the second one. Okay, now we are trying to find the distance from the center of the lens, right? So cc2, this will become r2. Fine, and then this will become r1. Okay, so these are the 2 points. That is, we have cc2 to be r2 and cc1 to be r1. This much is fine. Then we have a different refractive index for the lens compared to that of the medium, right? So we'll assume that medium is mu1, so even this will also be mu1, and this will be mu2, right? So we have mu1 and mu2 as the refractive indices of the two media whatever is present here. Then let's assume that there is some object here on the principal axis O. Then a ray of light first meets the first surface and then it undergoes a refraction in the lens. Then once it is coming out of the lens, again it undergoes refraction. So there are two refractions which is happening here. So first thing is from O to some particular part of the first surface. So this is the first refraction, right? So this is, let's say it's going here, and then from this point again it undergoes a refraction inside the lens. So let's say it's going something like this. And then once that is done, it comes out, again it undergoes refraction. Let's say it's coming here. So what we have is, let's say this point is A, this point is B, and let's say this point is I. So from A to B and then B to I. So this is how the actual refraction goes. Now suppose, let's say the second surface was not present, meaning xp2y was not there, then the ray of light would have gone undeviated, meaning the ray of light would have gone in this direction, correct? So what we have here is we have a point I1. So this is the undeviated ray. Now why that undeviated ray is important? Soon you'll understand why. Okay, so these are the things what we have as of now, right? Now we need to calculate different angles here. So different angles will come and then different criteria will be there. Okay, now first important thing is, remember in the previous video you did refraction through spherical surface. Now what was the formula for that? That was minus mu1 divided by u plus mu2 divided by v is equal to mu2 minus mu1 divided by r. Correct? So this was the formula for refraction through any spherical surface. So we are going to do the same for two surfaces, that is xp1y and xp2y. Okay, now we'll go with the first one. Now for the first surface, if you try to do here, what we have is, see, the ray of light is coming from mu1. So we have mu1 divided by P1O, right, plus mu2 divided by P1I1. P1I1 is equal to mu2 minus mu1 divided by P1C1. Okay, I'll repeat this. We have mu1 divided by P1O because P1O is the object distance, and then for the second surface P1I1, because what we are assuming here is a very important point, that is we are assuming that xp2y is not present, meaning the second surface is not present. The entire thing on the right side is just mu2. This is why we have the undeviated ray. Okay, so what we have is mu1 by P1O plus mu2 by P1I1, which is the object, the image distance, is equal to mu2 minus mu1 divided by P1C1. Now all the distances are measured from the center, and since P1 and C are very close to each other, we might as well write P1O as CO. So we have mu1 divided by CO now plus mu2 divided by CI1 is equal to mu2 minus mu1 divided by CC1. Okay, so we have this particular equation. Okay, so call this as equation number 1. Now we have first equation. Now for the second surface, what we are doing is, see, we have xp2y as the second surface, right? Now here I1 acts like a virtual object for the second surface. Okay, I'll repeat this again. I1, so this particular I1 acts like a virtual object for the second surface xp2y. Okay, so the ray of light is coming from the virtual object and making I as the actual image. Okay, so since we are talking about a virtual object, now remember I1 is a point in the second media, right? It's in the second medium, so that's very, very important. So since it is in the second medium, so we'll write I1 is a point in mu2. Okay, so this mu2 is very important. So since this is in mu2, now what we have to draw is minus mu2 divided by P2 I1. So from P2 to I1, because we are looking at the second surface now, plus mu1 divided by P2I, because the actual image is formed here in mu1. So we have plus mu1 by P2I is equal to mu2 minus mu1 divided by P2 C2. Okay, so this is what we have. Now since P2 is also very close to C, what we get is minus mu2 divided by Ci1 plus mu1 divided by Ci is equal to mu2 minus mu1 by Cc2. So we'll call this as equation number 2. Okay, now what we have is we have two equations, equation 1 and equation 2. Now we add these two equations. So what we are doing is we are doing 1 plus 2. Now if you look at this, so what we have is mu1 by Co plus mu2 by Ci1 minus mu2 by Ci1 plus mu by Ci is equal to mu2 minus mu1, take it as common, into 1 by Cc1 plus 1 by Cc2, right? So these two will get cancelled. So you just end up with mu1 by Co plus mu1 by Ci is equal to mu2 minus mu1 into 1 by Cc1 plus 1 by Cc2, right? So this is what you have. Now once you apply the Cartesian sign conventions, remember Co is minus U, because if you look at it, it's in the opposite direction. So Co is minus U, Ci is plus V, R1 is positive, R2 is negative, right? So if you apply that here, so you get mu1 divided by minus U, so minus of this by U, plus mu1 divided by V is equal to mu2 minus mu1 into 1 by R1 minus 1 by R2. Correct? Now, divide the entire equation by mu1. So if you do that, you have minus 1 by U plus 1 by V is equal to mu2 by mu1 minus 1 into 1 by R1 minus 1 by R2. Fine. So we divided by mu1. So that's why we get this equation. Now, if you look at this, remember by length derivation, what is minus 1 by U plus 1 by V? That's nothing but 1 by F. So we end up with 1 by F is equal to, now mu2 by mu1 is nothing but the relative refractive index. So mu minus 1 into 1 by R1 minus 1 by R2. So this is what we call as the lens maker's formula, because if you look at it, it gives a relation between the focal length F, correct? So this is the focal length, and then it gives the relation of R1 and R2, right? So it links between R1, R2 and F, and even the refractive index. This is the reason it's called as lens maker's formula. Because if you know the radius of curvature of the two surfaces and the refractive index, you will get to know the focal length.